When two sports cars speed down a highway at identical velocities, matching their pace with a camera makes them appear locked in place. The wheels blur, the road streaks by, but the cars themselves seem motionless. This visual trick exposes a core principle of physics. Absolute motion is a mathematical illusion. There is no such thing as being truly at rest. How fast an object is moving depends entirely on the vantage point of the person measuring it. In kinematics, we call this vantage point a frame of reference, a specific coordinate system paired with a clock that an observer uses to measure the world around them. Usually, when a physics problem gives you a generic velocity, it is defaulting to the Earth as an unstated, stationary reference frame. It assumes the observer is standing firmly on the ground. But tracking multiple moving objects from the Earth's frame requires setting up a separate position-time equation for every single object, and then solving those independent equations simultaneously. As you add more objects, the math scales into a tangled mess of variables. Relative motion functions as a mathematical methodology used to reduce multi-body chaos into a single-body equation. Adopting a perspective known as relative rest allows a student to freeze one moving target and force the rest of the system to mathematically adjust. For competitive exams like the JEE, this frame shift is a significant tactical advantage. To execute this shift, we first define relative velocity. It is the rate of change of position of object A measured entirely with respect to object B. This gives us the bedrock vector formula for one-dimensional relative motion. VAB equals VA minus VB. Consider this top-down view of a same-direction physical scenario. Car A moves to the right at 15 meters per second, while car B moves in the exact same direction at 10 meters per second. If we shift our frame of reference into car B, we subtract car B's 10 meters per second from both vehicles. Car B's velocity drops to 0. Car A's relative velocity is now 5 meters per second. To the driver in car B, car A is simply creeping ahead at that reduced rate. Now consider the opposite direction scenario. Car B reverses course, traveling to the left at 10 meters per second, creating a negative velocity on our x-axis. By applying our formula, VA minus VB, we subtract a negative 10 from 15. The mathematical expansion results in adding the magnitudes together. From car B's perspective, car A is now approaching at 25 meters per second. The physical intuition is straightforward. Locking your coordinate system to observer B requires subtracting B's velocity from every other object in the system. In this newly created frame of reference, object B is mathematically stationary. It does not move. This vector transformation allows us to quantify exactly how fast any object appears to move from any moving observer's point of view, bypassing the ground speed of the Earth. We can apply this relative velocity formula directly to collision and overtaking problems to strip away unnecessary variables. Within the relative frame, a collision has a strict definition. It is the precise moment the relative displacement exactly equals the initial geometric separation between the two objects. In this scenario, car A and car B are placed on an x-axis, separated by a distance of 900 meters. In the ground frame, they move toward each other at steady speeds of 1 meter per second and 2 meters per second. To solve this efficiently, we execute the frame shift. We subtract car B's velocity from the entire system, forcing car B into a state of relative rest. Because they move in opposite directions, car A's relative vector mathematically combines the two speeds. Car A now holds a single relative velocity of 3 meters per second. The 900-meter gap between them is now closing at a single, highly predictable rate. The calculation is immediate. Time equals relative distance divided by relative speed. 900 divided by 3 yields exactly 300 seconds. Staying in the ground frame would require plotting two independent position-time equations, equating them and solving for t. The relative rest strategy avoids that entirely, reducing a complex two-variable collision problem to a basic time and distance calculation. When we transition from constant velocity to variable acceleration, the math scales, but the logic remains identical. We define relative acceleration as the time derivative of relative velocity. AAB equals AA minus AB. The same frame-shifting subtraction logic applies to these second derivative vectors. Resolving the two independent acceleration vectors into a single relative vector places one object at relative rest, while the other bears the combined acceleration of the system. This leads to a critical threshold for advanced physics problems, calculating the minimum distance, or closest approach, between two accelerating bodies. This requires a core calculus principle. A mathematical function reaches its minimum or maximum value at the instant its first derivative equals 0. This is a graph of relative separation. The distance between the two bodies, s_rel, is minimized at the exact instant their relative velocity, v_rel, is 0. Geometrically, this is the exact bottom of the trough. The slope of the tangent line is 0, marking the precise moment the separation stops decreasing and begins to increase. In physical reality, if a fast-chasing car hits the brakes, the gap between it and the lead car continues to close until the exact millisecond the two vehicles' speeds match. Locating this v_rel equals 0 timestamp is the universal analytical anchor for solving any collision avoidance protocol. Once you have that time, you have the minimum distance. Now we scale the kinematics up to a three-body system, with multiple objects interacting on a single one-dimensional track. There is a strict methodology for multi-body interactions. Collisions are solved as discrete, sequential piecewise events, solving for one impact to find the initial conditions for the next. On the left, tracking this in the ground frame results in overlapping quadratics. On the right, the relative frame allows us to cleanly sequence the interactions, solving pair AB and then pair BC. Warning tone. This is where procedural errors can derail a calculation. The first error is the sign convention trap. Forgetting to establish a rigid positive x-axis direction before subtracting vectors will invert the relative velocity and compromise the entire solution. The second error is frame mixing. It is a logical fallacy to combine a ground frame velocity with a relative frame distance in the same equation. The third error is applying standard equations of motion without verifying that every variable, velocity, acceleration, and displacement, has been explicitly converted to its relative equivalent. Rigorous consistency in frame selection and sign convention is the primary defense against the mathematical complications of multi-body kinematics. Let's summarize the core rules for one-dimensional relative motion. For objects moving in the same direction, subtract their speeds. For objects moving in opposite directions, add their speeds. A collision occurs when the relative displacement equals the initial gap, and the minimum distance of approach always occurs precisely when the relative velocity hits 0. Relative motion operates as a vital strategic tool for variable reduction, simplifying the coordination of multiple moving parts. Mastering the shift in observer perspective allows us to consolidate multi-body systems into a single, elegant kinematic description.